In this video, we will see the remaining properties of d block elements. In the previous videos, we discussed about the properties like variation in atomic and ionic radii, ionization enthalpy, variation of melting point and boiling point, variation of density, and variation of oxidation states. Now, here we will discuss the remaining properties of d block elements. Now, the sixth property of d block element is magnetic property. The sixth property is magnetic properties. Now, we know that when a magnetic field is applied to a substance, two types of magnetism is observed, diamagnetism and paramagnetism. Diamagnetic substances are repelled by a magnetic field, and paramagnetic substances, they are attracted by a magnetic field. Now, if the substance is strongly attracted by a magnetic field, then we have ferromagnetism. And these transition elements, they mainly form paramagnetic behavior, or they show paramagnetic behavior. So, the question, why transition elements or d block elements show paramagnetic behavior? The answer is due to the presence of unpaired electron in d orbitals. So, the d block elements show paramagnetic behavior due to the presence of unpaired electron in the d orbital. Now, this unpaired electron in d orbital is associated with a magnetic moment. Magnetic moment denoted by mu, and the electron associated with a magnetic moment is associated with its spin angular momentum. So, the magnetic moment is determined by the number of unpaired electrons, and we can calculate the magnetic moment using the spin-only formula. And what's the formula to calculate the magnetic moment? Mu is equal to root into n into n plus 2 Bm. Bm stands for Bohr magneton, and small n is the number of unpaired electrons. Now, a single unpaired electron, suppose n is equal to 1, then we know that mu is equal to, how will you find mu? If n is equal to 1, then the magnetic moment mu is equal to root of 1 into 1 plus 2, which is equal to root 3, which is equal to 1.73 Bohr magneton. Now, the magnetic moment mu increases with increase in the number of unpaired electrons, or the value of magnetic moment increases with increase in number of unpaired electrons. So, as the number of unpaired electrons, the value of magnetic moment also increases. Or the magnetic moment value, if you know the magnetic moment value, then you get an indication about the number of unpaired electrons present in the atom. Now, let us do two questions. The first question is, calculate the magnetic moment of a divalent ion in aqueous solution if its atomic number Z is equal to 25. So, we know the element with atomic number 25 is manganese. So, what is the electronic configuration of manganese? Manganese is argon 3d5 4s2. Now, you are asked to find the magnetic moment mu of a divalent ion, which means two electrons are lost from manganese. It becomes Mn2 plus. So, Mn2 plus is the divalent ion of manganese. So, what will be the configuration? Configuration will be argon 3d5. Now, how many unpaired electrons in d orbital? There are 5 unpaired electrons, means n is equal to 5. So, how will you find mu? Root of 5 into 5 plus 2, which is equal to root 35, which is equal to 5.92 Bohr magneton. So, you got the mu value as 5.92 Bm. And if you know the mu value, you can also predict the number of unpaired electrons. 5.92 bm shows that there are 5 unpaired electrons in Mn2+. Now the second question, calculate the spin-only magnetic moment of M2+ ion whose atomic number is given, Z is equal to 27. You have to calculate the magnetic moment mu of element whose atomic number is 27. And you know the element with atomic number 27 is cobalt. So let's write the electronic configuration of cobalt. Cobalt is argon, 3d7, 4s2. You are asked to find the magnetic moment of M2+ ion. So cobalt will be in which oxidation state? CO2+, whose configuration is argon 3d7. Now when we say 3d7, how many unpaired electrons are present? 1, 2, 3, 4, 5, 6, 7. So there are 3 unpaired electrons. So small n is equal to 3. So how will you calculate mu? Mu is equal to root of 3 into 3 plus 2, which is equal to root 15, which is equal to 3.87 Bohr magneton. Okay, so this is the second question. Now the next question is, among divalent cations, divalent cation means with 2+ charge, in the first transition series, which element exhibits maximum paramagnetism? So among the divalent cation in the first transition series, the element that exhibits maximum paramagnetic behavior is manganese, because we know Mn2+, it has 5 unpaired electrons in the d orbital. So it's highly paramagnetic in nature. Okay, so this is about the paramagnetic behavior. Now the next property is property number 7, that is the catalytic properties of transition elements. So property number 7 is catalytic properties. Now we know that the transition elements, they can act as a catalyst, and what is the reason why these transition elements can act as a catalyst? That is the ability of transition elements to adopt multiple oxidation state, and also they can form complexes. So these are the 2 reasons for a transition metal to act as catalyst. The first reason is they can adopt multiple oxidation states or variable oxidation states. And the second reason is ability to form complexes. These 2 properties allow a transition element to act as a catalyst. An example for transition elements acting as a catalyst is vanadium pentoxide. Vanadium pentoxide is V2O5. This is used, vanadium, you know, it's a first transition series element, and vanadium pentoxide is used in contact fuses in the manufacture of sulfuric acid. Now next example, finely divided iron is used in Haber's process in the manufacture of ammonia, and nickel is used in catalytic hydrogenation. Hydrogenation means addition of hydrogen to double bond. These are examples where transition elements are used as catalyst. And we have also studied how the catalyst help in a chemical reaction. Now what happens? Catalysts, they form a bond. First the catalyst form a bond with the reactant molecules on the surface of the catalyst, and this in the catalyst, if it is a first transition series element, then the orbitals that take part in bond formation is 3d and 4s orbitals, or electrons present in 3d and 4s orbitals are used for forming bond. Now as a result, there will be increase in the concentration of reactants on the surface of catalyst. An intermediate compound is formed and the activation energy is lowered, and what happens? We know that the intermediate complex formed is unstable, so it decomposes to give the product, and the catalyst is regenerated back. And we know which property of catalyst helps in forming this bond with the reactant molecule. It is the ability of the catalyst to take variable oxidation state. Now we have an example to study. Iron 3. Iron 3. Iron 3 means iron in 3+ oxidation state. Iron 3 catalyzes the reaction between. So iron 3 is used as a catalyst. It helps in the reaction between iodide and persulfate ion. Iodide ion is I- and persulfate ion. Persulfate ion formula is S2O8 2-. So let's see how this iron 3 catalyzes this reaction, that is the reaction between iodide ion and persulfate ion. Now in the first step what happens is the ferrous iron 3, that is Fe3+, will combine with I- to form Fe3+, will get reduced to Fe2+, and I- gets oxidized to I2. Now when you balance this equation, it is 2 I- and 2 Fe2+. So this is step 1. This is step 1. That is the catalyst form a bond with the reactant I-. Now the next step you can see 2 Fe2+ formed will combine with the persulfate ion, and Fe2+ gets oxidized to Fe3+, plus persulfate ion gets reduced to SO4 2-, sulfate ion. So you can see in this step the Fe3+, which acted as a catalyst, is regenerated back. Now let's write, this is step 2. Now let's write the overall reaction. Now the overall reaction will be, you can see Fe3+ and Fe3+ gets cancelled, same way Fe2+ gets cancelled. So the overall reaction will be 2I- plus S2O8 2- gives I2 plus 2SO4 2-. So this is an example where the Fe3+ ion catalyzes the reaction between I- and persulfate ion. So the reason for the transition elements to behave as a catalyst is that it can adopt variable oxidation state, also it can form complexes. So the 7th property, that is the catalytic property, is over. Now the next property is formation of interstitial compounds. So property number 8. 8th property is formation of interstitial compounds. Now, what are interstitial compounds? They are compounds which are formed when small atoms like hydrogen, carbon or nitrogen are trapped inside the crystal lattices of metals. So we know in the crystal lattice we have voids or holes present. So interstitial compounds means in these holes or voids small atoms like carbon, hydrogen or nitrogen are trapped, and we get interstitial compounds. So these interstitial compounds, they are non-stoichiometric compounds, and they are neither ionic nor covalent. And an example for interstitial compound is TiC, then Mn4n, VH 0.56. These three are examples for an interstitial compound. Now let's see the physical and chemical characteristics of this compound. I told you these are neither ionic nor covalent. So let's see the properties of these interstitial compounds. They have high melting point, higher than those of pure metals. The second property is they are very hard. Some borides approach diamond in hardness. Third is they retain metallic conductivity. And the last property is they are chemically inert. So the transition elements, you can see the examples. The transition elements usually form interstitial compounds. Now the 9th property of transition element or D block element is alloy formation. So the 9th property, alloy formation. Now, what are alloy? An alloy is a blend of metals prepared by mixing the components. Alloys may be homogeneous solid solution in which the atoms of one metal is distributed randomly among the atoms of the other. And these transition elements, why they can form alloys? The answer is because of similar radii. Almost same atomic radii, the transition elements can form alloys. And example for alloy is ferrous alloys. Ferrous alloys are usually used to make steel and stainless steel, ferrous alloys. And ferrous alloys, they are a mixture of chromium, vanadium, tungsten, molybdenum and manganese. And these ferrous alloys are usually used in the preparation of steel or stainless steel. Now, also we can have alloys of transition metal with non-transition metals. For example, brass. Brass is an alloy of copper and zinc. Now, we know that zinc is not considered as a transition element, and we have already discussed because zinc has no unpaired electron in the d orbital in the ground state or in common oxidation state. So, zinc is not considered as a transition element. So, this brass, which is an alloy of copper and zinc, is an example where a transition element can form an alloy with a non-transition element. Now, these two can form an alloy because of their similar radii. Another example is bronze. Bronze is an alloy of copper and tin. Now, this copper and tin also have similar atomic radii. So, alloys, transition elements can form alloys because of their similar radii. Now, the next property of transition element is formation of colored ions. So, the next property number 10, formation of colored ions. Now, we can say that these transition elements, they form colored ions, and the reason for this color of transition metal ions is due to DD transition, that is electron present in the T2G orbital based on crystal field theory. The electron present in T2G orbital can get excited to EG orbital, and the color that we see is the complementary color of the light absorbed. So, the color of transition metal ions is due to DD transition. Now, only if there are unpaired electrons in the d orbital, DD transition is possible, and only those metal ions are colored. Now, if the d orbital is empty, if it is empty or completely filled, then no DD transition is possible, and we can say that compound or ion will be colorless. So, only if there is an unpaired electron in the d orbital, then that metal ion will be colored. Now, we have a question, that is zinc sulfate or scandium 3 salts and titanium dioxide is white in color or colorless. Now, what is the answer? You have to check the electronic configuration of these metal ions. Zinc sulfate means zinc has +2 oxidation state. You know the configuration, Zn2 plus will be argon 3d10. Now, this is colorless. Why? Due to completely filled d orbital. Completely filled d orbital. Now, the next is scandium 3 salts. Scandium 3 salts means we have scandium electronic configuration as argon 3d 1,4s2. Now, scandium 3 salts means scandium 3 plus configuration will be argon, which means any d electron unpaired? No. So, this is also colorless because it has a stable noble gas configuration. Now, the next one is titanium. What is the oxidation state of titanium in TiO2? Oxygen is -2, titanium will be +4. So let's write the electronic configuration of titanium. Titanium 4+. Titanium is argon 3d2 4s2. Now titanium 4+ will again take the configuration argon. So empty d orbital, or no dd transition is possible in scandium 3+ and titanium 4+. So they are colorless. So this is about the color. Now the next property, that is property number 10, is formation of complex compounds. Now, we have already discussed transition elements are capable of forming complexes. And what is the reason for this? Transition elements capable of forming complexes or coordination compounds. This is due to the comparatively smaller size of the metal ions, their high ionic charge, and the availability of d orbitals for bone formation. So these are the three reasons. First is small size of the metal ion, high ionic charge, and availability of d orbitals for bone formation. So these are the different properties. The 10th property is formation of complexes. So with this we complete the properties of d block elements. Thank you.